All right. Welcome everyone to for today's rendition of the point distribution webinar. Thank you very much for coming. Today we have speaking with us Professor Robert McCann from the University of Toronto, talking about maximizing angle sums between Euclidean lines.
Okay. Thanks. Thanks for the invitation. This is not my usual. This is a bit out of left field for me, and so this isn't my usual community or my usual topic. So that it'll be fun to meet some new people. So I'm going to talk about joint work with Tong-Suk Lim of Purdue University's Krannert School of Management. And there's a version of my slides posted on my webpage under the Talk 3 button in case you want to go back and look at an earlier slide. So the problem that I'm going to talk about is, you have, for example, if you have two lines in Rn and you want to maximize the sum of the angle between them, the best thing you can do is make them orthogonal. And if you have three lines in the plane, you get a little bit stuck because you can't, the third line you put in can't be orthogonal to the first two. And so, but in R3, you can have three lines that are all mutually orthogonal, but if you put in a fourth line, you get stuck again. So it's not so clear when the number of lines is larger than dimension +1, it's not so clear what configuration of lines is going to minimize the sum of the angles. And another way to think of this, since the lines, we're not dealing with oriented lines, so really this is a problem in the projective n-dimensional sphere instead of Rn+1. So you can think about trying to place k charges on the projective sphere, and you can think of the charges as repelling each other by a force that's central, so they want to move away from each other until they get to points that correspond to orthogonal points on the unit sphere in Rn. And then if you move them further, they would repel again and come back. And so another way to think about this problem is you're trying to find a globally stable configuration of k charges on the projective sphere, which are repelling each other with a pairwise force independent of distance, pairwise central force independent of distance. Great. And so this problem actually goes back some 60 plus years to a conjecture of Fayes-Toth from 1959 that some of the people in the audience have worked on. So his conjecture was that the best thing to do is to make distribute the lines as evenly as possible over some orthonormal basis. And so, if you have 100 lines and you're in R3 or S2, projective the 2 sphere, you would put 33 lines on, say, 2 of the basis vectors and 34 lines on the third one. And that's as evenly as you can distribute them. And the claim is that that will maximize the sum of the angles between them. And as I tried to illustrate, when k is smaller than dimension +1, this is sort of obvious. And and even in the plane, when you do this, as soon as you get 3 lines, the maximizer isn't unique, and there's many inequivalent ones. So the first two have to be orthogonal to each other, but the third one, the larger you make the angle to one of them, the smaller the other one gets, and so it compensates. So you can put the third one down anywhere. The fourth one has to be orthogonal to the third one, but the two orthogonal pairs you can put anywhere you like. Well, no, I guess, okay, yeah. So there's no sense in which this conjectured maximizer is unique. And you can even approximate the uniform distribution if k is large enough in the two plane. So we, since the problem is 60 years old and presumably hard, we thought, let's try to change it, let's study a simpler related problem. And so we thought about the case where the force is variable and increases with the distance. And so somehow I drew the potentials here. So the original potential is generating the constant force would be the red guy, whose derivative is constant. And we decided to look at powers of the angle, which were larger than 1, so that the force would increase with distance. And so a typical guy is the blue guy I've sketched. And the limit as this power b goes to infinity, I've normalized it. I've divided the angle by pi to normalize it. I probably should have divided by pi over 2. But yeah, so the pi should be a pi over 2. so the limit as b tends to infinity, the repulsive exponent tends to infinity, is a potential which is 0 unless you're exactly orthogonal. So you don't see the other charges at all except unless you're exactly orthogonal, and then you get a reward of 1. So that's somehow the limiting potential of this normalization that I've written down. Are there questions about this? Please feel free to stop me at any time and ask for questions if there are questions. Okay, so let me just introduce some notation. To get the projective n space, I just identify antipodal points on the sphere. And as I said, I'm going to divide by pi over 2 so that my normalization will be that the distance on projective n space has a maximum. The diameter of projective n space is going to be 1. And I'm going to generalize the problem a little bit. And instead of just thinking of k point masses sitting on the n-dimensional sphere, I'm going to think about the limit k goes to infinity and general measures, probability normalized to have mass 1. So I'm going to be looking at probability measures mu on the n-dimensional projective sphere, RPN. And my notation for that space of probability measures is script p. And in order to make contact with the original problem, I'll also think about the subset of measures which consist of k points equally charged. So my notation that will be this p subset k super equals for the fact that the mass on each point is equal. And then in this language, you can reformulate the Fayes-Toth problem from as the problem of maximizing a certain quadratic energy, where the kernel in my energy is given by this power b of the, of the this power b of the projective distance normalized so that the projective sphere has its diameter 1. So I'm going to be studying this problem for various b, and of course the original case is b equals 1. And the Fayes-Toth conjecture basically says that a standard basis, which by the way, that's when you look at the standard basis vectors, that's the largest simplex, convex simplex that you can have on the projective sphere. So it's the maximal projective simplex. And the Fayes-Toth conjecture says that if you just distribute the charges over each of these k vertices as equally as you can, so I've done k mod d, that will achieve the maximum in this energy maximization problem. And the conjecture is that this achieves the maximum when b equals 1. But if it maximizes for b equals 1, then it also maximizes for all larger b. And so you might expect it to achieve the maximum for every b between 1 and infinity. And well, we can't show it for every b, but we can show it for a large set of b's. So here's the first theorem that we can prove, which is that so fix k larger than dimension plus 1, then there's some threshold strictly less than infinity, such that the conjectured maximizer from the previous slide actually is the maximizer if and only if b is larger than or equal to this threshold. So we say there's some phase transition somewhere between 1 and infinity, and it happens before you get to infinity. Unless the conjecture is true, then then the phase transition would be at 1. And moreover, the conjecture maximizer is the unique maximizer if and only if you're strictly larger than this threshold. And so of course the Fayes-Toth conjecture is basically is equivalent to showing that this threshold is equal to 1. And notice that in case n plus 1 happens to divide the number of point charges, then the conjectured optimizer is placing equal mass 1 over n plus 1 on each of the vertices, and then it becomes independent of k. And so you can also conjecture that this thing, the thing that's independent of k, the equal distribution over the n plus 1 vertices, is the maximizer if you look at the set of if you look at all probability measures, not just those that are finite sums of point masses. And so we have a second theorem about that situation as well, namely that if n plus 1 divides k, then there's another threshold. And moreover, we get the stronger result that the conjectured optimizer in that case is the maximizer over the full set of probability measures when you're larger than the threshold, and uniquely if and only if you're strictly larger than the threshold. And so we put a preprint on the archive with this result, and then we heard from various people in the audience, Dmitry Bilik and Ryan Matsky and Alexei Glazherin and Hosea Park and Alexander Blasiak, and they said, we were very interested to see your preprint, and we have an argument that your threshold is actually no larger than 2. So this was very pleasant. And we reworked, after we got their note, we worked hard to show that actually not only is it no larger than 2, it's strictly smaller than 2. So we somehow recombined our ideas with their argument, with their estimate. And we were very happy to get that B was strictly smaller than 2 and not just say equal to 2, this threshold. So the threshold is only for the limiting problem. If we want to deal with a finite sum of point masses and the point charges are not divisible by n+1, then we still don't know the threshold. We don't have any bounds. We don't have any explicit bounds on the threshold. We just know it's finite. Okay, are there maybe before I go on, I should ask, are there questions about the statements? Okay, and so let me say why we were happy to be able to show that B was actually strictly less than 2. Eventually I'm going to talk about the proofs of these results, but before I try to say anything about the proofs of the result, let me say why 2 was sort of an important psychological value for us. So before I studied this problem, Lim and I worked on a different problem, which has to do with the what's sometimes called aggregation dynamics or attractive repulsive potentials. So we studied particles in Rn that are repelling each other when they're close together, they're attracting when they're far away, and what can the equilibrium look like? And we also looked not only at finite sets of particles, but also at measures under such an interaction. And from these kind of interactions are used in a wide range of sort of biological and other applications where, maybe the organisms the bacteria or whatever, they don't want to be too far apart, but they don't want to crowd each other either. And then what kind of patterns do you get forming? And it turns out that the answer is exquisitely dependent on the explicit form of the repulsion and attraction. You can get lots of different patterns forming, local minima and global minima. And so one of the results that we knew about from this area was a result. So I'm now going to talk about a different problem, and I apologize, on this slide and the next one, the signs are all flipped relative to the previous 2 slides. So in this context, I'm going to talk about minimizing instead of maximizing. And I hope that won't be too confusing, but minimizing a different energy. And this problem is set on Rn instead of the projective sphere. But a result that we knew about from 8 years ago was by Balaguer, Carrillo, Laurent, and Raoul. And they said, if you look at an attractive repulsive potential given by a difference of 2 power laws, so that the profile of the radial profile of the potential will look something like, it depends on whether A and B are positive or negative, but if they're positive, it'll look something like this. And I've chosen my normalization so that the particles want to be 1 unit apart. And if they're negative, it'll look something like that. But again, the minimum's at 1 unit apart. And so Balaguer and collaborators had a very nice argument saying that there's a lower bound on the Hausdorff dimension of the set of the minimizer as soon as B is less than 2. And so since in the Fayes-Toth conjecture, the repulsive parameter B is equal to 1, you would expect, if the situation were the same on this projective sphere as it is in Rn, you would expect that the minimizer would have Hausdorff dimension at least 1, which is quite different from what Fayes-Toth conjectured. I mean, to fix ideas, you can think of the attractive potential as having exponent A, and I'll just show you a sketch of the Balaguer and al. Argument. So they looked at this difference of 2 power laws, A, say, being 2 and larger than B, and what the Euler-Lagrange equation for a energy minimizer of this quadratic energy, mu convolved with W integrated against mu, says is that if you look at the potential convolved with the measure, the optimizer is going to have the property that all of the support, all the mass of the optimizer is going to be exactly where this convolution is a minimum. So the convolution W star mu might look like this, and then the support of mu is in here. And who knows what it does in other places, but the support of mu has to be in the minimizing set. And in particular, if A is 2 or something, if the A is growing in infinity, that's going to tell you the minimizers have compact support. And now if I look at the Laplacian of this potential x to the v in Rn, what I get is basically x to the v minus 2 plus a Dirac mass. And as long as I'm always going to assume that b is bigger than 2 minus dimension. I had that on the previous slide. Of course, when b is equal to 2 minus dimension, that's the Coulomb case, and then this term goes away, and I have Poisson. I have the fundamental solution to Poisson's equation. But sorry, my computer is telling me messages that I don't want to know right now. These potentials in this range, these potentials are subharmonic, and so the constant here is positive. And so actually, I know that this Laplacian is bigger than this power of x. And so now let me turn that around and let me integrate that power of b minus 2 of x against the putative optimizer. And this is in the range of b's that I'm looking at. This coefficient is positive. And what I see from this previous computation is that's less than Laplacian of this convolution. And what I see from the Euler-Lagrange equation is that this minus this is constant on the support of mu. So where these integrals are being computed, the Laplacian of that is equal to the Laplacian of this. And when a is 2, this is pretty smooth, and so its Laplacian is bounded, and so this is finite. And then there are results from harmonic analysis that say if you have a singular integral, when b is less than 2, this integral is singular. The strength of the singularity tells you the finiteness of a singular integral tells you that the mass of mu can't be too concentrated, otherwise this integral would blow up. And in particular, what it tells you is that the Hausdorff dimension is at least 2 minus b. And so somehow in Euclidean space, as soon as b becomes less than 2, the mass can't concentrate on points anymore. You can't assign a positive fraction of the mass at any point. On the other hand, what our theorem shows is that on the projective sphere, for some b, at least a little bit less than 2, it's still true that the best thing you could do for this minimizer, where, I mean, you're rather maximizer, where you maximize x to the b. And of course, we don't have a potential a in our problem, but all x squared is doing is it's kind of confining the mass. You could replace this potential a with convolution with some set and ask if the points are repelling each other with a force, say independent distance, and they're all confined to live in a particular maybe ball or square cube or something in Euclidean space, Carrillo and all are going to tell you that they're not going to concentrate on points. They're going to be on a set of Hausdorff dimension at least 2 minus b, and that turns out not to be the case in the sphere. So for us, that somehow was part of the interest of these results. Okay, are there questions? Okay, so I've restated the two theorems that I described before, and I'm gonna spend some time talking about the proofs then. So actually, these theorems are pretty easy to prove, except, so the only hard part to prove is the only if statement. So in other words, what is this only if telling us? It's really telling us that at the threshold, when equality holds here, there have to be other minimizers besides the conjectured ones. And that's the only delicate or the only technically involved part of the proof, is to show that there are other minimizers besides the conjectured ones at this threshold where the phase transition happens and the behavior of the optimization problem changes. We certainly know there are other minimizers when b equals 1. And so the question is there some larger b for which there are other minimizers besides the conjectured one or not? And we don't know, but we know that if there are any larger b's, they can't be even as large as 2. Okay, so apart from the only if, how does this proof go? Well, we've normalized the projective distance to be between 0 and 1, and equality holds only if x is equal to y or orthogonal to y. And so if I raise this projective distance to any 2 powers, b and b plus something positive, the larger power is going to be smaller, and equality is going to hold only in these 2 cases. And the conjectured optimizer has its support in the equality set. And so this comparison tells us that if this conjectured optimizer actually is optimal for some b, it's also optimal for all larger b, and moreover, any other optimizer for this larger value of b can't be supported outside the equality set. And so so any other optimizer for this larger b has to have the same support as the conjectured guy, or else be a rotation of the conjectured guy. And once you know that all the mass has to live on the orthogonal basis vectors, it's standard to show that the maximum is going to be attained when they're all equal. It could do it by Perron-Frobenius, for example. There's a unique eigenvector with eigenvalue 1 for the quadratic form, eigenvalue 1 being the largest element in the spectrum, and by symmetry, that eigenvector has to be uniform. Okay, so more or less that's the story, except for the only if part. But it's the only if part that tells us that we can lower the exponent strictly, the threshold is strictly below 2, so that's some of the interesting part for us. Right, the non-uniqueness that we observed already in 2 dimensions for 3 lines tells you that this threshold has to be at least 1, as long as you have enough point masses. And moreover, the other thing that's not quite obvious about this theorem is that the threshold is finite. Maybe it happens at infinity, or maybe there is no threshold. And we had actually argued this in an earlier work, but in the same communication with Dmitry Bilik and his collaborators, they gave an alternate proof, which is very nice, which they were kind enough to allow us to show, to include in our paper as a separately authored appendix. And I'm going to show you their argument at the end if there's time. I think there'll be time. And they also said, well, in the k equals finite case, what you've proved is actually a consequence of a well-known, but not to us, because we're not, somehow I come from this background in geometric analysis, and I didn't know much graph theory, even though I taught graph theory once about a year back, or a year or two back. But it follows from a well-known consequence of an 80-year-old theorem of Turan, which basically says, so why does graph theory come into this? Well, in the case where we let the exponent, the repulsion exponent, go all the way to infinity, we don't see the other charges unless they're exactly orthogonal to us. So you can think of your k points as the vertices of a graph, and you're going to connect each pair of points that are orthogonal, and those will tell you the edges. And since if we're doing this in Rn plus 1, there can be at most n plus 1 points that are orthogonal to each other, which can be all mutually orthogonal. And so we can't have there'll be no complete subgraph with n plus 2 points in it. And Turan's theorem identifies that graph of k vertices, which has no cliques larger than, no complete subgraphs with more than n plus 1 points in them. And it's, what graph is it? Well, basically it says you divide up the vertices as evenly as you can. So, and into n plus 1 groups. There's a picture, I have a picture from Wikipedia of Turan's graph for 13 vertices and no complete subgraphs of more than 4 points. So you divide 13 into 4 groups, and you put the vertices as evenly as you can. So 3 of the groups are going to have 3 vertices in them, and the 4th group is going to have 4 to add up to 13. And then you connect each vertex to all the guys that are not in its group. That's Turan's graph. And Turan says that's the best, that will give you the most edges for this number of vertices and no cliques larger than n plus 1. And most number of edges tells you largest number of points, pairs of points are orthogonal to each other on the sphere, and so that will maximize our limiting energy. Okay, so this is the argument that tells you these thresholds are finite, both when k is a finite number n in the limit, or when n plus 1 divides k. And so now we've actually proved the theorems, except for the only if part, except for showing that the set of optimizers for the limiting problem, which we now know to be the conjectured set of optimizers, is a strict subset of the set of optimizers for the threshold problem. Any questions? Great. So the last half of my talk is going to be devoted to showing the strict inclusion happens at the threshold, and maybe talking about 1 or 2 consequences of that. So to show this strict inclusion, we're going to prove another result, which is also of some interest, which is that if we don't insist on global energy maximization, we can also study the possibility that there are local optimizers, local maximizers for this problem. And we're able to show that the conjectured optimizers are actually local maxima for all b strictly larger than 1. So we get all the way down to the conjectured best value of b, the conjectured threshold value of b, if we're willing to settle for local optimality instead of global optimality. However, when you want to talk about local optimality, at least in the limiting problem when k is infinity, if we're looking at the whole set of probability measures, there's lots of different topologies you can put on the set of probability measures, and it's not at all obvious what topology you should mean in order to have local maxima. And in fact, this isn't even obvious for finite k. It's less obvious than you might think, and maybe we'll see why in a second. And so I need to talk about what kind of metrics you can hope to have local maxima in. And so now we are on my home territory, but maybe it's not everyone else's home territory, which is the theory of optimal transport. So what is optimal transportation? So you have two distributions of mass, and you have a cost for moving a point in one distribution to a point in the other distribution. And the question is, how can I rearrange the points in the first distribution to get to the second distribution so as to minimize the total cost or the expected cost or the average cost? And so often you see this problem formulated in Euclidean space, but you can formulate it actually in any metric space. And here we're going to want to formulate this transportation problem on the projective sphere. And so given two probability measures, mu and nu, on the projective sphere, one way of formulating this problem is you can look at all joint measures, say, on the sphere across itself, projective sphere across itself, such that the projection onto the first copy of the sphere gives you mu, and the projection onto the second copy of the sphere gives you nu. So in other words, the marginals of gamma are prescribed to be mu and nu. And among those joint measures gamma, you can just try to minimize the expected value of the projective distance to the pth power. And if you take the pth root of this minimum quantity, then what you get is a distance in the sense that it satisfies the triangle inequality. And the distance is 0 if and only if mu is equal to nu. And it's symmetric. And this definition works perfectly nicely as long as p is strictly less than infinity. We're also going to need the case p equals infinity. So you can define that in a limit if you like. Or you could also say, another way of saying this is, I'm going to look at all random variables x distributed like mu and y with law nu. And of course, those random variables x and y can be correlated in lots of different ways, basically parameterized by these joint measures gamma down here. And I'm going to choose that pair of variables that minimizes the LP distance between x and y, random elements, I guess you'd call them, random vectors, whatever, on the projective sphere. And that this definition would make sense out of the can for p equals infinity. So I can try to choose my random variables to be correlated so as to minimize the L infinity projective distance between them. And that's the metric that's going to be of the most interest to us, because it turns out that for every finite value of p, these guys all metrize weak convergence of measures on the sphere. So they all lead to the same topology. But for p equals infinity, they lead to a richer topology. And a richer topology means more open sets, and that means it's easier to have local maxima. And this was home territory for me because when I was a PhD student at Princeton in the early 90s, the very first problem I studied was I was trying to do mathematical physics. And I asked my advisor, Elliot Lieb, for a problem to study, and he suggested that I think about the problem of rotating stars. And so what was rotating stars? So you can think about a star as being modeled by a large distribution of gas. And it's maybe a little bit of gas here is attracted to a little bit of gas there by, say, Newtonian gravity, which wants to make it all collapse to a point. But on the other hand, it obeys an equation of state. So there's some pressure. If you try to squeeze it down to a point, it pushes back against you. So, and finally, it's kind of swirling around. And so there are at least three contributions to the energy of such a gas, namely the Newtonian gravitational potential energy, the internal energy associated to the pressure, and any kinetic energy due to macroscopic motion of the gas. And you might think that the shape of the star would be given by trying to minimize the sum of these three energies, subject to constraints on like the total amount of mass. So you could normalize, you could represent a star by a probability density if you wanted in R3. And maybe subject, you want maybe the total momentum around, so you want maybe fix the center of mass so it has no linear momentum. And the total angular momentum will also be constant. But it turns out the bad news is that unless the total angular, if you fix the total angular momentum to be 0, then, and you make some assumptions about the form of the pressure, then indeed you can show that there's a unique minimum, and it will be a spherically symmetric distribution of gas with the densest gas in the middle and progressively lighter as you reach the surface of the star. But if the angular momentum is not 0, there's no global minimum. And so the best you can, what I showed in my thesis is the best you can hope for our local minima. And even to get local minima, you need a very strong topology, namely the d infinity topology, except it would be on Euclidean space instead of the projective sphere. But and why do you need such a strong topology? Well, so if the angular momentum is large, you expect to find stars in the form of binary systems where the two stars orbit each other. And I guess I didn't tell you why you can't have a global energy minimum. Maybe I should say that. You can always take a teaspoonful of mass and put it in orbit very far away, where it can orbit very slowly and have enormous angular momentum. So you can totally satisfy the angular momentum constraint by doing that. And but it's orbiting very slowly, it has very little, and it's a teaspoonful, it has very little kinetic energy. So if there's a positive kinetic energy, which there needs to be in order to have a finite amount of angular momentum, you can always reduce the energy by the kinetic energy by a factor of 2 by taking a teaspoonful of mass and putting it far away where it carries, making a satellite that has all the angular momentum and very little kinetic energy. And then you can stop the rest of the star from rotating, and so you win energy that way. And similarly, if you have a binary system, you can always win by taking a little bit of mass from the lighter component and evaporating it and moving it to the heavier component instead. So if mass has a way of tunneling from the lighter component to the heavier component, you can always lower the energy by shrinking the lighter component and making the heavier component heavier, and they get further apart. But you can never attain the minimum. If you take the limit of this process, what you get is the non-rotating minimum with 0 angular momentum. It doesn't satisfy the angular momentum constraint anymore. But in this d infinity topology, you can have local binary star systems become local minima. Why? Because d infinity prevents you from evaporating mass on the lighter component and putting it down on the positive component, on the other component. Because no matter how little mass you evaporate here and give birth to there, that is the distance of this epsilon perturbation is the distance between the two components. It's not going to 0 no matter how small epsilon is. And that's the kind of topology you want in this kind of problem. And both in the rotating stars problem and in this Phaeus-Toth problem, if you want to talk about local optimizers. Okay, are there questions about the topology? Right, so here's our next theorem. Not only are the conjectured guys local optimizers, but any measure that has that support is also a local optimizer. So let's look at weighted versions of the conjectured guys. So you pick your favorite. You have a binary star of any mass ratio you want if the angular momentum is large enough, and it will be a stable local minimum. Similarly, here you can pick any set of masses that add up to 1, and you can look at this linear combination of Dirac masses or convex combination with these convex coefficients, and then the claim is choose a lower bound epsilon on the minimum amount of mass. I've ordered the masses, so m1's the minimum. And as long as my repulsive exponent is bigger than 1 plus epsilon, there'll be some radius that depends on dimension and epsilon, such that any mu that's within this radius of this guy here has energy less than that guy, or else is a rotation of this guy. So in other words, this thing is a strictly local maximum except for its rotation. This guy, the orbit of this guy's rotations form a strict local maximum for this problem. And of course, somehow this radius is like the radius of the basin of attraction on which this is a strict local maximizer, and that radius is going to degenerate to 0 if you let epsilon go to 0. So if you evaporate all of the mass on one of the components, you don't have a local maximizer anymore, necessarily. At least this argument doesn't tell you to, and I wouldn't expect it to be. Certainly it is. Okay. certainly it isn't in the analogous problem in Rn, which I talked about with the attractive repulsive potentials. Okay, so we have this theorem about strict d-infinity local maxima, that even these unbalanced guys form strict local maxima on a small d-infinity neighborhood of themselves. Yeah, I have to say this issue about part of the difficulty of these problems is the invariance of the energy under rotations, which rules out a lot of techniques that would work. It tells you the energy can't be convex, for example, in any usual sense of convexity. Okay, so why is this theorem relevant to, I mean, of course it's relevant, but why is it relevant to the original theorem, which was this only if part of the threshold result, the claim that there were other optimizers of the threshold repulsion exponent? Well, so let me just describe how this works. And it's actually easier to make the argument in the case where K is finite. So when we're dealing with finite number of point masses. So then, because what's special about a finite number of point masses is actually when you restrict, so we, of course, sorry, I just lost where I was. Right. When you, if we're dealing with the whole, I need a pencil again. If we're dealing with the whole space, RPN, then as I said, d infinity gives you a different topology than dp. But if we're dealing with pk equals, it turns out that then I've taken this continuous problem and made it discrete. Then the topology of d infinity is the same as topology of dp. Because when I fix k, I can't evaporate a little bit of mass here and give it there. I have to do it in discrete quantities, 1 over k. And so I've quantized the problem somehow. And then all these metrics, dp for every p, including infinity, give you the same topology. So, so if I imagine now I look at the threshold energy, I subtract epsilon from the threshold. So now I'm in the case by construction, unless the threshold is 1, unless the conjecture is true. If the threshold is larger than 1, I can always subtract epsilon from it. I can take a minimizer of that perturbed problem, and I know it won't be the conjecture guide because that's how the threshold was defined. And as epsilon goes to 0, of course, projective space is compact, and D2 gives you the weak metric. So I can extract a limit of these measures on projective space as epsilon goes to 0. And according to general gamma convergence techniques, you won't be too surprised to learn that the limit of these measures for the approximating problem is still a maximizer of the limiting problem. And what we wanted to prove were that there were maximizers for the limiting problem that were not the conjectured guys. Well, and I claim that this mu naught, which was a limit of the mu epsilons, is not one of the conjectured guys. How do I know? Well, I know that the conjecture guys are these strict local maxima from this theorem. So what does that mean? It means that I can't even, if I get close to one of these conjecture guys, then the energy inequality is going in the wrong direction. Somehow that's the flavor of the argument. And now things are a little more subtle if I want to do this on the whole space where the topologies are different, because it's still true that the mu epsilon is going to D2 accumulate to mu naught, but I don't know any mu naught is not, I don't expect the conjectured guys to be D2 local maxima. I only expect them to be D infinity local maxima. And so then I need an additional argument to say that because these guys are maximizers, I can study the Euler-Lagrangian equation, and from the D2 convergence, I can eventually deduce D infinity convergence. But it won't necessarily, it'll be D infinity convergence to one of these local maximizers, but it won't necessarily be to the balanced one, to the equally weighted guys. And that's why it's really useful to know that not only when the MIs are equal to each other, but even when they're different from each other, I get a local maximizer. Great. So basically I get that I'm going to show what this local stability property allows me to deduce is that there's some vector m hat for which mu epsilon the infinity converges to. And then once, so I know in the end, I know all the mass of mu zero is supported on an orthonormal basis. I don't know what weights it has, but in fact, even it might not be exactly an orthonormal basis, but it's approximately an orthonormal basis. And then once it's approximately an orthonormal basis, you know that you do better by making the vectors, you increase the energy by making all the vectors exactly orthogonal to each other. And then you increase the energy again by making all the weights on them equal to each other. So that's somehow the argument. Okay. And so I also need to tell you, how did we prove that these unbalanced guys, orthonormal bases, are still local, d infinity local energy maximizers? And somehow it relies on this following lemma, which has the flavor of control of the L2 norm by the L1 norm. So what does it say? It says, so for any c less than 1, there's a radius bigger than 0, such that if you take n probability measures, which are very close to being Dirac at n different orthogonal basis vectors, then you can find a point near the n plus first basis vector, such that this is something like the W star mu we saw earlier. Except I flipped a sign here. I mean, I should be convolving maybe the pth power here, but anyhow, the bth power of the distance. I flipped the sign so that this potential here is going to be minimized when x is on the equator of y. And if I add up these contributions from the n different y's, then somehow this is going to be minimized on the intersection of the n equators. Except the y's aren't exactly an orthonormal basis, because I have all these probability measures that are just close, concentrated around n orthonormal basis elements. And so somewhere near the n plus first element will be a point that minimizes this. And around the minimum, this energy, because it's the 1th power of d, this energy has like a V shape. And when you add up all these V shapes, you get something like the L1 norm around the minimum, and that dominates any multiple less than 1 of the L2 norm around the minimum. So as long as x, oh, now I'm confused. I think there's a typo here. So this x bar is approximately xn plus 1. And I'm honestly not sure if this should be x bar or xn plus 1 here, but when the distance of x to one of these guys is small enough, then I get this domination. And what this lemma basically tells me is, now imagine that you have some mu naught or mu epsilon close to mu naught. So what do I know about the mu epsilon? I know that most of its mass is concentrated near, say, these could be 3 basis elements in R3. So I have stuff here and stuff here and stuff here. And what I want an energetic argument that says, let me take the stuff here and concentrate it at a single point, somewhere near E1 hat, and leave the other stuff the way it is. I want to know, how does the energy change? And the energy changes in 2 ways. So if I choose the right point here, I can hope to improve the interaction energy with this stuff and this stuff. And this lemma tells me how much I can hope to improve it, because the interaction energy of this point with this stuff and this stuff is given by a sum like this. It'll be, those will be weighted by the amount of mass at each endpoints, but that's okay. So there'll be some mass factors in front of here. Now so I can hope to win a little bit by concentrating to a point, except I also lose because before, the angles of all these lines were contributing something to the total angle sums, and when I concentrate at a point, they're now contributing 0. And so I have to balance the amount that I win against the amount that I lose. But the amount that the amount that I lose is somehow proportional to d to the b, where b is bigger than 1. And this inequality is telling me the amount that I win is proportional d to the 1. And for b bigger than 1, d to the b is always less than d to the 1. And somehow that's the flavor of the argument that tells me that I can win a little bit of energy by concentrating at this point. And once I've done that, I win a bit more by concentrating all the mass up here at some other point near this basis element. And I win a bit more by concentrating all this mass here. And then I'm in better shape. And that tells me that these points, these x bars, there's one near each of these guys, if I apply the lemma n+1 times, are almost an orthonormal basis. And from there, I can argue my way out. All right, are there questions about the argument? So finally, I can give you, so I've already given you two pieces of evidence towards the Fayes-Toth conjecture, which is, first of all, the conjectured optimizer is still optimal when B is less than 2, a little bit less than 2. And so already we see the difference between the sphere and Euclidean space there. And secondly, the conjectured guys are strict local maximizers. They, in their rotations, form a strict set of local maximizers for any B bigger than 1. And now there also, as a consequence of these results, you can also see that if you studied a curve of optimizers parameterized by B, at the threshold, that curve is going to have to jump from this non-conjectured optimizer to the conjectured optimizer as you pass through the threshold. So this curve has to be a discontinuous function of B at the threshold, except possibly as B equal 1. And finally, a similar thing, if I look right at the threshold and I look at the set of all optimizers, I know it's got to be d-infinity disconnected, because the rotations of the conjectured guys form one set of optimizers, and I know they're strict local optimizers, so there's a neighborhood around them that's empty of other optimizers, but I know there's some other optimizer outside that neighborhood. And so unless B equals 1, I know there's some value of B, namely the conjectured guy, the threshold guy, at which the set of optimizers is going to be d-infinity disconnected. All right. So we're almost, yeah, we're almost out of time. I guess I have a couple minutes left. So let me in the last 2 minutes, try to sketch the argument of the quintet that shows that this threshold actually can't be any larger than 2 when k is divisible by n+1 or in the limit. And so so basically, you know, we're trying to maximize theta over pi by 2 to the power b. But theta is, after all, the arc cosine of the vector x dot y, where x and y are points on the Euclidean sphere, or the projective sphere embedded in Euclidean space. And so I drew here in red, or rather Desmos drew the arc cosine. This is normalized, so this is like theta over pi over 2 on this axis. And this is, or rather, maybe it's theta on this axis, it's 2 over pi arc cosine to the bth power. The 1th power is in red, the square power is in blue, the 4th power is in green, and I want to compare that to the function 1 minus t squared, which is the guy in black. And of course, the red guy has infinite slope at where it crosses the origin, but it has a quadratic singularity, so the slope remains infinite if you raise it to a power less than 2. It becomes finite when you raise it to the square power. This guy has finite slope here, so basically the exponent 2 is the first time that this function has a chance to be underneath this function, and it turns out that it is underneath that function as soon as b is 2, and it gets further underneath it when b is larger than 2. And some of the fact that this guy is underneath this function when b is equal to 2, and notice equality holds only at 0 and 1, so only for points that coincide with each other or orthogonal to each other. This inequality here is what drives their bound, that what they're able to show is that when b equals 2, the only optimizers are the conjectured guys. And what we were able to show is that at the threshold, there have to be other optimizers, and therefore the threshold must be less than 2. And so on my last slide, I gave the rest of their argument. Here it is. So you take this arc cosine function, you can rewrite the energy in terms of it. Let me call that f. And from this, by integrating this inequality, I know that when b is 2, my energy is less than this f when I use the function g, which is 1 minus t squared. And moreover, the conjectured optimizer lives in the equality set, so E2 is equal at fg. So these two inequalities are straightforward. And what Bielik and collaborators told us is that this inequality and this one are known. And so basically, for example, you could take a uniform measure, or you can also take the conjectured optimizer, and those guys both maximize f for this particular g. So this apparently is known from the theory of frames, and it's not hard to prove, and so here's a proof. Let's define the moment of inertia tensor of mu. And then, of course, when I want to integrate g, I really just need to focus on t squared, which is x dot y squared. And the integral x dot y squared against mu mu is basically the trace of the square of this moment of inertia tensor. And so the Cauchy-Schwarz inequality for the matrix Hilbert-Schmidt norm tells us that trace is bigger than the trace of the inertia tensor squared with a factor which is basically the trace of the identity matrix. And moreover, it tells us equality holds here when this moment inertia tensor is a multiple of the identity matrix, and it will be a multiple of the identity matrix for the normalized surface area and also for the conjecture guy. So that's how you get these two intermediate inequalities. And now I think I've actually gone 2 minutes over time, so it's probably a good time to thank you very much and for your patience and stop for any questions that might have come up.
All right, are there any questions for our speaker? I have at least one question, Robert. Maybe you explain this. What is the justification that you know that threshold has to be at least 1? How do you know that it can't be less than 1?
Right. So so let me go back. But it's this only if statement again. So well, basically the justification is that when b equals 1,
Mm-hmm.
when k equals 3 and n equals 2, we know there are other optimizers.
Mm-hmm.
And so from that, you can also deduce that when b equals 1, for other k's and n, there will be other optimizers other than the conjectured guy.
Mm-hmm.
But our theorem tells us that if you're larger than the threshold, there can be no other optimizers.
Right.
So basically from the non-uniqueness of the conjectured optimizers at b equals 1, we know the threshold can't be any smaller than 1.
I see. Do you have any idea in the case where b might be less than 1, what might be possible optimizers in those cases?
We haven't thought about b less than 1, so.
Okay. Other questions?
Yeah, I have a quick question. Do you have a guess as to which other energies may have the same optimizer, so the periodically repeated orthonormal basis, or what's for the discrete energy? Or, well, in other words, what is the main property here that makes?
Sorry, one of us is having trouble with our internet connection. I just but I'm now working. Your question was?
Can you hear me now? Hello, can you hear me? Ryan, do you hear me?
I hear you, yes.
Yeah, I hear you too. I was just muted.
Oh, okay. Right. So my question was basically, what's your guess? Which other energies may have the same type of behavior, the same type of minimizers, like the periodically repeated orthonormal basis for the discrete energy? What do you think is the important feature of the kernel here?
Yeah. Well, for us, I mean, so because I came at this thing from, I mean, the only related work that I'd done previously, apart from the stuff on rotating stars, was this business about attractive repulsive potentials. And so for us, this somehow was kind of like an attractive repulsive potential where the repulsion is the explicit part and the attraction comes from the fact that I'm in a compact set, that's localizing it. Yeah. For things that are, I mean, even among but somehow even among attractive repulsive potentials, at least in the Euclidean problem, you get lots of different patterns forming. It's really not, I mean, somehow there's lots of numerics showing lots of different patterns. The number of mathematical results is much smaller because really the only things that you can establish mathematically are you can identify situations which a uniform distribution is going to solve the problem. You can identify it now with my work with Lim, and you can identify situations in which maybe a simplex is going to solve the problem. where all the guys are at the preferred distance from each other. There are not so many mathematical results. I mean, what people do is like local stability analysis around conjecture things, and so there's more things about what are local optima. But even in that problem, we don't really understand what determines the shapes terribly well. So I mean, somehow I have even less intuition about this problem. Maybe you probably have more intuition than I do.
I don't know. So let me also restate the question a slightly different way. For which other kernels, for which other energies would what you're doing in these papers would also work?
Right. I'm sorry. I'm too inexperienced in this area to hazard a guess.
That's okay. Yeah, it's a heuristic question. No, that's
Sure.
Yeah. Yeah. Okay. Thanks.
I mean, I know people look at these frame energies, and I have just absolutely no intuition into them because I'm not very conversant in this literature, and this is a bit of a venture into left field for me.
Thank you. Yeah, and it's nice to finally meet you. Also.
Yeah. This is the best we can do at the moment.
Right. Yeah. Hopefully we can do better soon. Yeah.
Any other questions for the speaker?
Have we stopped the recording? Are we still recording?
Oh yeah, let me stop the recording.